This is a quick video on how to use the solutions from solving an ODE numerically to create an animation and also to explore an animation with a parameter. Let's get started. This is a classic problem of a one-dimensional problem in the vertical direction. You fire a ball straight up in the air. It not only feels the force of the earth through gravity, but it also is experiencing air resistance as proportional to the speed squared. There's our ODE as written out. There is our initial condition starting at some initial height with some initial speed. We make sure all our constants are pre-assigned, and then we solve using dsolve, producing the list of procedures. As before, we extract out the procedure of interest. In this case, it's the position. And since the ball is traveling up in the air, we're interested in at what time does it come back and hit the ground again. Now comes the part that we want to know. We are going to use the animate procedure from plots. We are going to animate a plot. To animate a plot, you need within the square brackets from here to here all the information that you're going to put in our plot. Our plot consists of essentially watching a single point that has no x position and has a y position that changes with time. So this is the only point within a list of points. Our style is of point. You could have used point plot, but I like to use it this way. We're going to have a symbol which is a solid circle, and if symbol size is 30, we could make it any color. Once we establish all those parameters within the plot, now we can change the parameter that is telling you about the animation, that is the time. It goes from 0 to t final. Finally, we put some options in for animate that is useful. We're going to put in 100 frames, and we're going to make sure our animation is of this particular size. When I hit enter, I create the animation. You can see the little plot down here. I click on it, I go up to the top, I hit the play button, and it goes up in the air, turns around, and comes back down. The previous plot was useful, but on the other hand, it was not plotted in real time. Since we know we're going to be running at 10 frames per second, if we multiply the amount of time it takes for it to travel by 10 frames per second, that will give us the number of frames that is going to be in our in our animation. So we'll add that in. I'll re-enter, and now it does last within the 3 seconds and is plotted as in real time. Here's another version of the same thing, but now we're going to explore the animation, because what I want to do is, how does this drag coefficient from the air resistant affect the height which the ball goes up, and essentially the time it takes for it to reach the top and come back down. It's exactly the same problem as before, but you may notice that I have removed the constant c. I have not assigned its value. Instead, we're going to use the parameterized constant, include the fact that c is a constant. Now I hit solutions, we've solved it, and I extract my solution. Now comes the fun part. We have to write a procedure that we are going to show the animation, but in the procedure, we change the value of c depending upon what our slider does. Here is the procedure. It's going to be passed a dummy constant. This is the constant that our slider is going to be sending from the Explorer procedure. We're going to call the solutions that we already have nynum. These are well known globally. This line is not necessary, but it makes it more readable. And essentially, we're going to, locally, calculate the amount of time that the ball is in the air. Because the process basically consists of the following. The Explorer procedure is going to pass it some variable, some net value for c. We're going to set our solutions to that variable. From it, of course, we will therefore calculate the final time at which the ball reaches the ground. Finally, the objective here is to animate our solution, so it's exactly the same procedure call that we called before, except what I've done with frames is I've put all the calculations of the number of frames within this part. Now we add in the Explorer procedure, calling it myAnimate. There is the letter C. The C is the parameter within the slider that we want to change as part of our drag coefficient. We hit enter. The drag coefficient can go between 0 and 0.1. Let's say right now it has no drag coefficient. You can see the vertical height, and we can click on it, push play, and you can see the ball go up in the air and come back down. This is, again, all in real time because we added this calculation right here. Unfortunately, what it does is it keeps bouncing up and down. So let's actually add some drag. We could either stop it like right there, or we can change the drag to some value. And as you can see, as I'm changing the value, okay, that the maximum height at which the ball can travel is much lower. Let's put it all the way to 0.1. Now I'll click on it. I'll push play. And it doesn't go up as far, and therefore is not in the air as long. Go to the link listed below, or go to gould.prof to find the document for this particular video.